Well, hello again. Okay, we've talked about the unit circle and a little bit about wrapping functions. Okay, once again, when we're talking about a wrapping function, the input is the length of the wrap beginning with the point 1, 0. The output is the ordered pair that you end up with on this unit circle as a result of the wrap. Okay? So a wrap of pi got us here to negative 1, 0. A wrap of pi over 2 got us here to 0, 1, so on and so forth. What about a wrap just to some arbitrary point in the first quadrant on the circle there? Okay? Well, it's not going to be very pretty. And it's not going to really come out nicely, and we don't have to worry about them for the most part. We're only concerned with those outputs, those ordered pairs on this circle that are the result of a friendly wrap, okay? Like a wrap of pi, or 3 pi over 2, okay? But there are other ones than just those wraps that land us on one of the axes, okay? There are wraps that are nice, sort of, at least to me they are, that end up kind of in here, okay, just between where the points are sort of off in one of the quadrants and not actually on an axis. It's all about angles. It's all about geometry, okay? If you think about it, there are really two kinds of special right triangles, 30, 60, 90 triangles and 45, 45, 90 triangles, which are also called isosceles right triangles, okay? And you've got to recall the way the sides of those triangles are related in order to derive some of these sort of stranger wraps in the unit circle, okay? So if we talk about a wrap that is the result of sort of a 60-degree rotation from this point, we want to know sort of the coordinates of that. Well, let's kind of jot this down. If this is a 60-degree angle, right in there, 60 degrees, we're trying to figure out the coordinates of those points. Well, first of all, you know this is a right angle here. Okay, if we kind of drop this right down here, we want to figure out the coordinates. Well, we know one of the three lengths of this triangle, right? You know that the hypotenuse is 1. Why? Well, because it's the unit circle. We've defined this circle to have a radius of 1. So no matter where that point is, the length of that hypotenuse in that triangle is going to be exactly uno, okay? Now, 1, the length of that hypotenuse, does not represent either x or y, right? The legs of that triangle do. This leg represents the x value of that point, right? Think about it. X tells you how much displacement, I guess, is going on, left or right of the y-axis, right? So at this point here, x is telling us how far to the right we are from this point. So this length here is going to be x, and this length here is going to be y. Okay? Think about special right triangles. Well, first of all, if that's 60 degrees and that's 90 degrees, by the triangle sum theorem, we know that angle has to be 30. So let's jot that down in there. And just remember from geometry, okay? It's all based on the smaller leg of a 30, 60, 90 triangle. You first want to find the smallest leg, and then you know the hypotenuse is twice that leg, and the other leg is the small leg times root 3. Remember that from, who knows, maybe you had me, maybe you had Mr. Grugan, who else might have taught geometry back then? Miss Grace, I don't know. Swope, you probably had Swope, didn't you? Well, Swope's the man. We shared classrooms next to each other our first year teaching, which was 2005. Gray hairs, all right? No, not because of Mr. Swope, because it's been 9 years since I've been teaching here, all right? Anyway, so if you remember special right triangles, back to what's important, the hypotenuse is 1. The smallest leg, that value is going to be 1/2. 1/2. Because the hypotenuse is always twice the smallest leg, okay? The smallest leg, which is always opposite the 30-degree angle, is 1/2. And this guy is the small leg 1/2 times root 3. 1/2 root 3. Well, that's better written as root 3 over 2. Okay? So the coordinates of that point are, let me replace the xy with, well, 1/2, comma, root 3 over 2. Now, that's the output, right? We've got to think about what the input would be. And that's a little bit confusing, okay? Well, we know we've come 60 degrees from this point, right? We've rotated 60 degrees to get there. And it's not drawn to scale. It looks like it's probably a little more than 60 degrees. But if that's 60 degrees to get there, think about, in terms of the circumference, what that value, what that input would have been, all right? 60 degrees. Well, remember, guys, that 180 degrees, we went from here all the way here. That was like pi, a wrap of pi, because the entire circumference was 2 pi. Right? We went 2 pi, our input was 2 pi to go all the way around. So our input is just pi to get here. Well, pi was 180 degrees, right? So 60 degrees is 1/3 of that. It's 1/3 pi, or pi over 3, okay? You don't have to remember where all this stuff comes from, to be honest. Special right triangles, you don't need to know that so much. But I did want to teach you guys where these values do come from. You're going to have to commit these to memory. You're going to have to really memorize these key rotations in the unit circle, all right? So I didn't want to just tell you that, over here, W of pi thirds equals 1/2 comma root 3 over 2, though that is true, all right? That's one of the key wraps. Not as pretty as like W of pi over 2, which is just 0, 1, all right? It's up there. It's at 1/2 comma root 3 over 2. But you're going to see these numbers repeat themselves a lot. Remember that this kind of a function, this wrapping function, is periodic. The values are going to repeat themselves a ton. Maybe one of them will be negative on this side in the second quadrant. Maybe they'll both be negative down here in the third quadrant. Maybe the x value is negative down here, and the x value is positive, but the y value is negative down here. But these numbers are going to come into play a lot, okay? So that is one example, all right? That's how to get a rotation of 60 degrees, which corresponds with pi over 3 in terms of the wrap, okay? And in a similar manner, guys, a wrap of what would be 30 degrees. If it was 30 degrees, it might be about here, right? 30 degrees, well, that's 180 over 6. So 30 degrees would correspond with a wrap of pi over 6, okay? If it was 30 degrees. And it's just that these guys get flip-flopped. For the same reason, you still have a radius of 1, so you can set up the same diagram, and these just get switched. So it turns out that we have root 3 over 2, comma, 1/2, as the result of a rotation of 30 degrees. So W of pi 6th, which is like 30 degrees, would get us root 3 over 2, comma, 1/2. Again, this is what's most important, that you really memorize this stuff, okay? But I wanted to show you guys where these come from and why they're important. I mean, if we're talking about a wrap of like something obscure, like 47 degrees, we could find that out, but it would take a lot more serious trigonometry and it wouldn't be so pretty. So we don't really handle those, okay? The key wraps we deal with are 0, pi over 6, pi over 3, pi over 2, and then they repeat, all right? And there's one more, okay? There's one more, which you guys can probably guess. What do you think? If we're in the first quadrant, what rotation do you think we might want to get to next? A half of 90, 45. That's the other kind of special right triangle you've dealt with. So let's do that right now. Sorry to have to erase this stuff. I'll leave the wraps on the board. Okay, talking about a wrap of 45 degrees. It's probably a little more accurate than my previous ones. All right, 45 degrees. Now, a 45, 45, 90 triangle, if you'll recall, well, let's drop this right down here. Again, this is going to be, we're talking about finding the ordered pair, right? Finding the ordered pair, that's our output. This, from here to here, is going to represent our, let me just clean this up. That's going to represent our x value of that point. The length from here to here. The y value will be from here to here. They've got to be the same. It's an isosceles triangle. But this is 45. So these guys are congruent. All right? So if the radius is 1, then, you know, maybe you set up an equation. This gets a little bit ugly. So then we even use the Pythagorean theorem in this case. All right? If we call this x. Because it's isosceles, we can call this x also, right? So let's just kind of take care of the Pythagorean theorem, a little reminiscent of your times with your geometry teacher. So x squared plus x squared is 1 squared. 2x squared is 1 squared, which is just 1. Divide by 2, we get x squared is a half. The square root of a half is going to be, well, the coordinate of both x and y, the square root of 1/2. Let's not worry about plus and minus, okay? When you're writing an ordered pair, it just kind of depends on what quadrant you're in to figure out the sign of each value of x and y. Up here, x and y are both positive, right? The square root of 1/2 is going to clean up the square root of 1 divided by the square root of 2. Root 1 is just City Line Avenue. No, it's just 1. Root 2, we have to just leave that. 1 divided by root 2, let's rationalize the denominator. And we get 1 times root 2. Root 2 times root 2 is 2. That's the key. That is another, wow, I wrote real slanty here, didn't I? That is another irrational value on the unit circle that's going to come up quite a bit is root 2 over 2. Like you see root 3 over 2, you see 1/2. Root 2 over 2 is the other one that comes up quite a bit. So our ordered pair there is root 2 over 2, comma, root 2 over 2. And we would write the wrap. You could probably figure this out. Again, 180 was a wrap all the way around to that side. So 90 was pi divided by 2, and 45 is like pi divided by 4. Okay, so a wrap of pi over 4, pi fourths, gives us an output, or the ordered pair of root 2 over 2, comma, well, root 2 over 2 again. Okay, anytime you're on the 45 degree, you're right there. They're going to have the same exact number, right? So these are the other key wraps, at least in the first quadrant. Every x and y coordinate we've dealt with in these 2 videos comes up again and again and again. Your answer is going to have one of those points. You've got to figure out the signs. That's the key. That's what's hard. Figure out the sign of x and y. Figure out where on the unit circle that wrap must fall. If we have a wrap of 7 pi over 6, well, that's sort of based on the pi over 6, right? You have 7 of these. Figure out where that's going to land, and that'll tell you, well, whether x is 1/2 or y is 1/2, or are they root 3 over 2 or negative root 3 over 2. You've just got to figure out where that lands, okay? And then you'll have your answer, all right? One more short comment. We often draw some rays here to indicate this kind of rotation. This ray is always called the initial side of the ray. Jot that down here. The initial side of the ray always cuts through the point 1, 0. So that's kind of new terminology. And the terminal side of the ray cuts through the point that we want to end at. Okay, the terminal side of the ray is the key, right? The initial side is always the same. The terminal side is what we're dealing with. Okay, the point on the circle that we're concerned with is always contained as part of the terminal side of the ray. All right? See y'all soon. Oh, it won't stop.